We have an exciting lecture today. You ready for this exciting lecture? It is very exciting as lectures go. Okay? So, what we're going to do today is we are going to transition to looking inside of members that have to carry moments. Okay? And I'm going to go ahead and give members that are in that category a name. Right? If we have a member that has been designed so that it has to carry an internal moment, we're going to call those members beams. Okay? This is a little bit different than members where they are designed to carry axial loads. Those are sometimes known as links. Other times maybe they're known as columns. But those kinds of members that carry axial loads are different than the kinds of members that have to carry these bending moments, because what it's going to lead to, as we're going to learn over the next few class meetings, it's going to lead to a different kind of stress that we're going to call flexural stress. We're getting started with that idea today by looking at internally inside of members that are carrying these moments, and we're going to try to figure out how we can quantify those moments, as well as another factor that is called a shearing stress. So if you want to put a big heading on today's lecture, you might say shearing forces and bending moments in beams. Okay? So the heading on this little part that I'm going to do right here, I'm saying internal influences carried in beams. Let's say I hadn't given you that introduction yet, and you weren't ready to, or you weren't sort of prepared and ready to hear something about bending moments in beams. Let's look and see if we could sort of figure out what goes on inside of these beams. Okay? And I've set up two kind of similar scenarios here. One is a concentrated load of 10 pounds acting right in the middle of a beam that's called a cantilevered beam. All right? If you ever see something where a piece of a beam is sort of hung out without a support on one end, and it's supported entirely from one end, right? That's usually an indicator that that is a cantilevered portion of that beam, just as a word that you know exists. Okay, so these are two cantilevered beams. One has a concentrated load of 10 pounds acting right in the middle. The other one has a distributed load of 1 pound per foot acting over the entire 10-foot length. Okay, and let's think about what the reactions would be in each of these cases at the support. Okay, so what if I was to do a little simplified free body diagram of this guy up here? Right, and another little simplified free body diagram of this guy over here. Okay, how would I have to draw things on that little free body diagram above the concentrated load version? Right, I'd have to show the concentrated load of 10 pounds. I'd have to show my 5 feet, right? And what would I have at the support? Okay, well, I would have to have something that would react against that 10 pounds, right? So if I wanted to, I could, just say maybe R sub y for the reaction there in the y direction. Okay, but what else? Someone mentioned it. Okay, there's got to be a concentrated moment like we saw the other day acting on this end to keep it from trying to rotate, right? Did I draw that the right direction? Okay, let me draw it the correct direction here. Let me draw it this way. Okay, and we could say, let's just call that M. All right, and based on this free body diagram, what is the value of each of those unknown variables I just found? We could do sums of moments or sums of forces, but it's easy enough for us to just probably inspect it and be able to tell. What is R sub y? Okay. R sub y is going to just be 10 pounds. And what is M? It'll be 50. Okay. Units? Foot-pounds. Great. You guys remember how that part works, all right? Well, what about my other case? All right. What do I do for my other case? What's my first step? Yeah, I can basically say this distributed load is equivalent to a concentrated load that I might show right here, right? What would the value of that concentrated load have to be right in the middle of that distributed load? 1 pound per foot times 10 feet, it would be 10 pounds. Well, once I've got that 10 pounds right in the middle, then that's how I would evaluate it on a free body diagram. And what would I have any different scenario here? Okay. M and RY, and this would still be 10 pounds. This would still be 5 feet because it would be right in the middle of where the distributed load was acting. Okay. I would submit to you that there would be no difference in the reaction at the support, which is really good because that's what I told you the other day, right? I said you should be able to lump all of this distributed load into a particular location located at the centroid of the distributed load, and that total load you could apply at that location with no difference in the reaction to the supports. All right? Well, that's all great, but what I want to do now is confuse this a little bit. Okay? What if I'm not looking at specifically at the support location? What if I would make a cut somewhere else? And just for the interest of clarity, let's just pick a point. I want to pick a point somewhere between where the distributed load, or excuse me, where the concentrated load is acting and the wall. Okay? So, where do you want to put it? I don't care. Okay? At 2 feet? It's like 2 feet from the wall. Okay? So let's just say that's where it's at. It's 2 feet from the wall. Okay? And if I make a cut right there, one of the things I can do is imagine making a, or not imagine, I could actually make a free body diagram up to that cut. I would still have my 10 pounds of force acting here. Okay? That's what I know. What kinds of influences should happen at that location where I made the cut? Okay? Well, for one thing, I have to react against that 10 pounds of force, right? And what would do that would be a shearing force that would act like this, right? And I'm going to actually give that a letter. I'm going to call that V. Introduce another kind of letter that we a lot of times use. V is a force value. We a lot of times, we'll use that variable for a shearing force, okay? And what else? Because if you think about this, it is 2 feet, right, away from the wall. So what does that mean in terms of this little length right here? Okay, this will be 3 feet. And because V and the 10 pounds are at 2 different lines of action, I'm going to have something else that keeps this from rotating. And that thing is going to be a moment. Right? And that moment and that shearing force are what I want us to try to find. Okay? So let's do the shearing force first. What do you think the value of V is going to be based on a sum of forces in the vertical direction? Okay? Again, V is just going to be equal to 10 pounds because it sort of has to be, right? It's the only other thing acting in the vertical direction. So it's reacting against that 10 pounds that's being applied. So that part's easy. What about M? Okay. M is going to be 30 foot-pounds, right? Fantastic. You guys are doing great so far. Okay. I'm going to go ahead and give each of those a name, right? This is the shearing force. And this is a bending moment. And I found it at some other location besides at the support. One of the reasons I wanted to do this little illustration for you is I can cut in the same location now for my original case, right? My original case before I lump the load, right? What if I make a cut in the same location there, still 2 feet away from the end? What would my free body diagram look like now for this case? All right. So I would draw something like this up to that location where we made the cut. Okay. Now what do I do with my distributed load? Okay. Keep in mind what the distributed load is doing is something like this, but it's only extending because I'm only taking a portion of this whole beam, right? It only goes up to the location where I have the cut. Okay. And so if it's only going up to the location where I have the cut, how would I evaluate this concentrated load? It would still be at the middle, right? Something like this, but it's at the middle of this little segment. Okay? So now we need to kind of think about this. We need to say, well, if that was 2 feet over there, then this is 8 feet. Agreed? And how much load do I have for this lumped load that I put right there at the middle of that segment? Okay. It's 1 pound per foot, which is what I had here, right? 1 pound per foot. And it's that times 8 feet, so this is just going to be 8 pounds, right? Okay. Well, what reactions do I have at the cut? Do they look any different? As far as what kind of reactions, they don't look any different at all. I'm still gonna have this shearing force that happens right there on that face where I made the cut, and I'm going to have a bending moment. But for this case, what are those values? What's V? And what's M? Okay. Yeah, in case you didn't kind of see that, you know, we have to look to the middle of where that load is lumped, and that's going to be 4 feet. Right? What we'll see here is that the load that I have at that location is not 30 foot-pounds. What's it going to be? 32 foot-pounds. What's our big takeaway from this little exercise that I just did? Okay, let me say it this way. When you lump a load to find external reactions, that's fine. You can certainly do that. You cannot lump a load to find internal reactions, okay? Because it's going to be different. What happens inside of this thing is not equivalent between one case and the other, all right? The only thing that's equivalent is what happens over at the end where it's being supported, okay? And I want everyone to kind of feel that, right? Because that's a key place where a lot of people make mistakes. Okay? That's one of my goals with presenting this little quick example. But my other goal was just get you used to this idea of making a cut and trying to come up with what the shearing force and the bending moments are going to be at that particular cut location. Right? So we picked a location. We said where it's going to be, 2 feet from the wall. Then we looked at the geometry to figure out how much particularly the bending moment is going to be one of the things that, you know, it matters where we made that slice to, you know, come up with what the bending moment is going to be. And then, of course, the conclusion that it's not going to be the same, that the shearing force and bending moments are not going to be the same everywhere we look in the member after having lumped the load. Okay? One more point I want to try to make on this before we leave it. Could I have made the location where I made the slice, could I have made that instead of just a fixed 2 feet? Could I have made it a variable? In other words, what if I had taken my original case here? Let me see if I can copy it, right? And instead of, you know, making this particular location where I make the cut right there 2 feet, what if I instead define a location where I can make the cut as X, and I make that value relative to the left end? Okay. Could I do the same thing that I did with a specific value, could I do it generally for any value? Okay? So for the left case over here, I mean, either case, the answer is yes, but for the left case, one of the things I have to do is actually define some domains, right? Some regions of the beam where one way of saying it is going to be valid, and then maybe it'll be different in another place. Let me show you what I mean by that. What if x, in this case that I'm showing you here, is less than 5 feet? What is v going to be? In other words, if it's less than 5 feet, that's a cut somewhere over here. What's v going to be? Okay. Here's what the free body diagram would look like. I put a v on here. I put maybe an m. That would be my diagram with no other applied loads. So what are v and m? 0. There's no loads for it to be carrying out there, as long as we're neglecting self-weight and that kind of stuff. Okay, great. What if x is between 5 and 10 feet? Okay. But now it's, we're going to go ahead and leave it with a value of x. We're not going to say exactly what x is. We're just going to say x is somewhere between 5 and 10 feet. Okay. Now what's different? I have my 10 pounds. I still have a v value that I'll put right here and an m that I'll put over here. What is v and what is m? V is still 10 pounds, but for m, it changes a little bit. And what we need to think about is how far is the line of action of the 10 pounds away from the cut, right? So for that, it would be 10 pounds times what? X minus 5 feet, right? Does that make sense? Could I do the same kind of thing for the other case? Okay. In other words, what if I took my original case that I had right up here at the beginning and I said, I'm going to make a cut instead of at 2 feet, I'm going to make a cut at X. What would that free body diagram look like? Okay. Well, now it's going to have this load all the way across. Okay. It's going to have a reaction here. It's going to have another, okay, so that'll be V, and we'll call this M. This is 1 pound per foot. And this is X. Okay, so the first step we can think about mentally is, again, lumping the load. Something like that. How much load is that going to be? Okay. It'll be X pounds, right? This is 1 pound per foot, so this will be X pounds. Do you agree with that? And how far is that line of action from the cut? Okay. It'll be, running out of kind of room here, but this will be X over 2. So what are my two values now? What's V? X pounds, right? Right? So wouldn't that be about right? And then M is going to be what? X squared over 2 foot-pounds. Okay? There actually might be some more units to take care of in those calculations. That's not what I'm trying to get you to focus on. I'm trying to get you to focus on, you can actually, think of this as a variable, and all the same steps you did with actual numbers still work, and now you can come up with a function that tells you shearing force and bending moment regardless of where you look along the length of the beam. You know, with one thing to say about that, though, in addition, and that is you also have to keep in mind that with any concentrated loads or any sort of changes along the length of the beam, you might have to divide it up into segments, right? And say, this is a function that works in this segment. This is a function that works in this other segment. Okay?
I was going to ask, with the first segment, it won't work once you go past the 5-foot mark. If you make a cut at 4 feet or 3 feet, because you'll get a negative moment, and then the 10 pounds won't be applied to that segment. Is that correct?
Okay, his point is, for the first example, you can't do it to the left of where the 10 pounds is being applied. And the answer is, you can, it's just not interesting, right? Because what you'll do is you'll show a reaction of V and M, but there won't be any other loads on that segment, right? That's what was the first little free body diagram I drew. I erased it now, but you know, there's no other forces besides just those two reactions that you listed, and so those two reactions aren't needed, right? So they're zero, and it's not interesting. So in other words, you know, not unexpectedly, there's going to be zero load over to the left of where the where that load is being applied. Okay. To the right is where it's more interesting. And that formula that we just came up with, you know, for V, just a constant 10 pounds. For M, 10 pounds times x minus 5 feet. Those formulas will work for any location in that segment from 5 feet to 10 feet. X equal 5 feet to 10 feet. Okay? So anyway, I'm trying to get us warmed up on this idea of what we're doing here. But before I do a big problem, which I'm going to do here in just a moment, I want us to spend a couple seconds thinking about something that's called sign convention. Okay? And I think one of the easier ways for me to talk about sign convention is to do another sort of conceptual example here. All right? So this conceptual example involves us having a beam that has two forces of 2 newtons acting on it, opposite directions, and two forces of 1 newton acting on it in opposite directions. Okay? And if you want, you can kind of go through the mental exercise of thinking about whether or not that body with those loads that I'm showing, is it going to be in equilibrium? Okay? So someone give me a reason why or why not. Is that body that I'm showing with those forces and those lengths, is it going to be in equilibrium? You say yes.
Because the moment around the very center equals 0.
Okay, the moment, you can look kind of by inspection, and if you draw a point right at the very middle, you would say, what effect are my 2 Newton forces going to have rotationally? Okay, 2 newtons times 1 meter plus 2 newtons times 1 meter, right? So how much total? 4 Newton meters, right? In a counterclockwise direction based on the 2 Newton forces. What about the 1 Newton forces? 1 Newton times 2 meters clockwise plus 1 Newton times 2 meters clockwise will exactly balance the other two, right? So this is a kind of a special scenario that I've got set up, but I'm doing it so that you can see what the response of the beam is going to be under this load. Okay? You'll notice that you know, you wouldn't be surprised, at least, if the way that the beam would want to start deforming is given with that little shape that I showed right below, right? It's going to kind of turn into a smiley face on the left, more like a frowny face on the right. See that? And you know, somewhere in the middle, maybe it's not curving at all. Okay. You guys are doing great so far. Here's what I want to do. I want to look at 3 particular locations and look at the free body diagrams. Okay? So the first place I want us to look at is, what if I made a cut basically at half a meter, okay, 0.5 meter over here. Okay? And I'll call that location 1. So here at location 1, what do my free body diagrams look like for my 2 halves of the beam that I cut in half right there? The left one looks like what? Okay, it'll have a 1 Newton force acting up right here. And what will it have at the cut? A downward V, okay, which would have to be 1 Newton. And then what else? Okay, counterclockwise moment, and if this is at, half a meter, like I said, then what's that moment value going to be? Any thoughts? Okay, 1 newtons times 5 meters, or 0.5 meters, it'll be half a Newton meter. Wonderful. What's the other side of this diagram going to look like? Okay, I might have to scrunch it down here just a little bit. What do I have here? 1 Newton. I'll have 2 Newtons here. Okay. And 2 Newtons here again, right? 2 Newtons. And then what do I have? If I had a 1 Newton downward shearing force on the left side, what do you think I'm going to have on the right side? Okay. By Newton's third law, it should be equal in magnitude, opposite direction. So if it was a downward 1 Newton force there, I should have an upward 1 Newton force here. Does that make sense with the diagram itself? Okay. I have downward 3, upward 2, right? So I've got 2 plus 1 going downward plus 2 newtons going upward. I need something to balance that. 1 Newton upward balances the 3 coming down and the 2 going up. Does that make sense? So that works. It says I've got an upward shearing force that happens right there. What would my bending moment do? Newton's third law would suggest what? Opposite direction around this point. Okay? It would suggest equal magnitude. This one would be a little bit harder for us to figure out, but it would still be the same thing. I would have a clockwise 2 times 1/2, right? So that would be 1. Then I would have a counterclockwise 2 times 2.5, right? So that'd be 5, counterclockwise. And then 1 times 3.5. And if you add all that up, it ends up being a half a Newton meter, just like we would expect going that direction. Okay? So, all that's kind of interesting. It lets us see what those free body diagrams would look like together if I made that cut at location 1. You got a question?
Your shear force on the second free body diagram.
Yep.
It's in the opposite direction. Oh,
It's in the opposite. Yeah, he said the shearing force on the right free body diagram there is in the opposite direction of the one that's on the left, which is exactly what we would expect by Newton's third law. Okay? And it is what we get. All right. Here's the point that I want to make. If you see a beam that has these reactions in these directions, in other words, downward for my shearing force on a left part, or a counterclockwise reaction on the left part, that is defined as a positive shearing force and a positive bending moment. Okay? So I'm going to say over here, our shearing force is positive, and our bending moment is positive. Okay? And the way you can always tell for this is that if the left piece wants to rise relative to the right piece, right? In other words, if all of a sudden you could just chop through it with an axe and like slice through it right instantaneously, what direction would the parts want to move? If they would want to move the direction I'm showing there, that is defined in our convention as being a positive shearing force. Okay? And the thing about conventions, what that basically means is that a whole bunch of people got together and decided this is what we're going to take as being positive. There's not some transcendental reason why. It's just everyone got together and decided, let's call this direction positive. And that way everyone calls it positive. Kind of like current convention, right? If you're in circuits class, everyone decides, you know, current flows from positive to negative, right? And they made a convention out of it. Kind of turns out they were wrong if you're thinking about electron flow, but now it's a convention and now we're going to use it that way, okay? But anyway, there's not really any being wrong about something like this. It's just what direction are we going to take to be a positive direction for our shearing force, and what direction are we going to take to be a positive direction for our bending moment. So that actually brings that up. For the bending moment, anytime you've got an influence that tries to bend the beam into a smile, that is a positive bending moment. This one's easy to remember, right? The smiles are positive. So just like we saw over there on our little diagram for our exaggerated deformation, it is smiling in that zone, and so that is, you know, a little bit of help for us to sort of believe that our answer is correct. All right, shall we do another location? What about location 2? I'll try to go a little quicker on this one. Okay, location 2, let's take location 2 to be the same kind of spot, but over on the opposite end. And I'll do a couple of Freebody diagrams there. Okay, there's 1, and here's 2. Okay, and so the easy one for us to look at first is the piece that's on the right. So I've got this 1 Newton force that comes down like this. What kind of force would have to react against that 1 Newton force to keep that little segment in equilibrium? Okay. Would it be upward? Okay. Wonderful. What about over here? Okay. If that one's upward, it probably means this one's downward, right? And if you go ahead and look through it, it's, you know, it does turn out that way. This is 1 Newton. This is 2 newtons. And this is 2 newtons. So you would imagine that we would need a 1 Newton reaction force in either of those cases. Okay, now what about my bending moment? Okay, I didn't write it over here, but let's say this is again 0.5 meters away from the right end. All right. What direction does my bending moment have to happen on the right piece to keep that in equilibrium? Would it be this way? Think about summing moments around the location where the cut is. In order to keep that in equilibrium, I need to counter the clockwise rotation that would happen from the 1 Newton force on the right end of the beam. So I'd have to counter that, and this would have to be a 0.5 Newton meter moment that would have to react against that one to keep it in equilibrium, right? Okay, and we could do the same thing on the other side. I'll you know, let you do the math if you're curious about it, but this should end up being a clockwise tendency to rotate of 0.5 Newton meters that kind of reacts similarly over there on the left side. All right, so let's think about our shearing force and bending moment. What's my shearing force? Basically, at this point, you have to answer, is it the same as I had on the left end, or is it different? directionally? It's the same, right? I still have a downward force acting on the left part. I have an upward force acting on the right part. So this is still a positive shearing force. But what about my bending moment? Okay, my bending moment here is negative. And it's, you know, you can see that. If you look at on that right side, it's frowning, right? So that's a negative bending moment. Again, these are just sign conventions. This is like we all got together and agreed that this is what we're going to call positive and this is what we're going to call negative. Okay? Well, does that mean that I have a positive shearing force across my entire body? What do you think? Shall we do one last location and try to see if that's true? Let's do a cut right in the middle. Okay. Give myself a little more room here. So a cut right in the middle. What would those free body diagrams look like? All right, I'm going to have half and half, right? So I'll show one half here and another half over here. Okay, I have 1 Newton here. I've got 2 Newtons here. All right. I've got 2 Newtons here. And I've got 1 Newton here. Okay. What direction do my shearing forces have to go at that cut location to keep both sides in equilibrium? On the left side, I need to go up, right? Because I have to counter, you know, I've got 2 coming down with 1 going up. It means I'd have to have 1 more going up to balance it out in the vertical direction, right? So 1 Newton meter here, or excuse me, not Newton meter, 1 Newton here. What about on the other side? Okay, opposite direction but the same value, right? 1 Newton there as well. Okay, so what direction is that shearing force? Okay, I'll say it's a shearing force that tries to make this go the other direction, right? The right side wants to rise relative to the left side. Okay, and that is a negative shearing force. Okay, now what about my bending moment? This one's actually a little bit tricky for you to think about. What are these lengths? I know that I didn't draw it perfectly to scale. How far is it from the 1 Newton force to the cut? Okay, it's going to be 1 meter to the 2 Newton and then another meter to the middle. So that's going to be 2 meters. And how far is it from the 2 Newton force to the cut? Okay, that one's just going to be 1 meter. Now what happens if I sum moments around the cut? Okay, it's a little bit of a special case, right? There's 0 bending moment right there at the middle of this beam. What if I move a little bit to the left or a little bit to the right? It's no longer 0. It's only 0 right there at the middle. But I figured I'd pick that point off and let you see that there are sometimes these beams that are being flexed like this, and there can be spots where there's 0 bending moment, right? By the way, there can also be spots where there's 0 shearing force, even though this particular example doesn't have that shown. So let me actually like color code this thing, okay? Anywhere I put yellow is going to be a positive bending moment. Okay, so that's positive M. Anywhere I put this blue color, that's a negative bending moment. So I'm going to put minus for that bending moment. So that part's kind of easy to see. Now what about for my shearing force? Okay. We said at first that there was a positive shearing force. So I'm going to use green and say there's a positive shear. What do you think happens right there where that 2 Newton force comes down? Okay. Well, we found a location between where those two Newton forces are acting, and we said in between those is going to be negative. And I'll just go ahead and tell you, you can extend that to that entire phase, right? All the way from here to here, you're going to have a negative shearing force. And then you're going to go back to a positive shearing force over there. Okay? Now, out of all of this, the main thing I want you to come away with is, I guess, a couple things. One, the idea that there are sign conventions that someone else made up and that we're going to try to follow, right? Frowny and smiley are the easier ones for us to understand. The shearing force, we kind of just have to memorize that if it's loaded in such a way that the left piece wants to rise relative to the right piece, that's a positive shearing force. Or if, and then the other case is if the right piece wants to rise relative to the left piece, then that's a negative shearing force. Okay? And we've got to have these in mind when we go to our big problem that we're about to try to solve. And you guys are excited, I know. You excited? Yes.
So everything else seems pretty clear here. The only thing that I'm not exactly grasping is assigning a positive or a negative shearing force. Like,
Okay.
what do we see that decides that?
Okay. So his question is, how did I know what direction to show these different arrows for upward shearing force versus downward shearing force? Is that basically the question? Yeah. Okay. I did it based on mental math, right? So I did it based on looking at the diagram and seeing, you know, on net, how much do I have pushing up, you know, versus down. And when I do all that, whatever I add onto there as the reaction had better balance out whatever was left, right? So for that very first one, I said on net, you know, for everything to the left of where the reaction occurs, everything to the left of that, I ended up with an upward 1 Newton force. So I better react against that with a downward 1 Newton force. That's all I did. And I mean, some of them, the ones where there's more forces, it's a little bit harder to do, but let's look at the right side, right? I have a downward 1 Newton, upward 2 Newtons. So that basically now I'm net up by 1 Newton, right? Then I go down with 2 more Newtons. So now I'm net down 2 Newtons. So that means I better react against that with an up 1 Newton. All right? Now, a much more formal way for me to do that same thing would have been for me to assign variables to show on those reactions and then do sums of forces in the vertical direction. We would have come up with the same conclusion. But I tried to make the numbers simple enough so where everyone could just see, you know, here's how these forces would end up balancing out without having to do the free body diagram with equilibrium equations.
So like, whenever we're trying to assign our positive or negative value, we basically ignore our reaction forces that we're putting at the brake and say on the left side we're positive, on the right side we're negative. And then because the left side's up and the right side's down, we assign positive.
Right. Well, at this point, so he's wanting to know how would I assign one versus how would I assign the other. At this point, all I'm trying to do is just define the two for you. That if it's trying to do one of the things, it'll be positive, and if it's trying to do the other thing, it's going to be negative. Right. And just define that those are going to be agreed upon to be the positive direction versus the negative direction. And then I'll show you how I'm expecting you to maybe apply that whenever we do this example problem. Does that sound good?
Sounds good.
You got a question? Okay, so he's saying when we work out the moment, do we always take our sum around the cut? And I would say, even though you might not absolutely have to, that is the best thing to do. Yeah. You could take a sum around some other location. It just complicates everything a lot. So yes, I would recommend you think of the moment being evaluated around the location of the cut. Okay? Because that is the location where we're trying to find the moment, right? That's what we're talking about with all this, is trying to figure out what those bending moments are at each of those locations. All right. Wonderful. Let's get on to our example problem. And I chose this example problem very intentionally, because one of the things I think is wrong with some ways of teaching statics is that we a lot of times start by giving you a diagram that just shows all these different loads that you have no idea where they came from, right? So instead of giving you that, I'm going to reinforce the idea here that when you're solving these beam problems, very often your beam problem might arise out of a frame and machine problem, right? And you get that frame and machine problem done. Now you know what forces are acting on the different parts. Some of those parts are beams. Then you might have to analyze those beams to figure out the internal shearing forces and bending moments. And once you know those, then maybe you can figure out how much stress is acting in those beams. And then after you figure out how much stress is acting in the beams, maybe you can figure out whether or not they're going to break, right? We're not doing that whole thing right now. I'm just showing you there is sort of a sequence to how you need to think about some of these problems, and they do originate in real-world scenarios often. So here is one. You can think of this like maybe a hamburger patty press, all right? Or if you're not into eating animals, you know, then there's a lot of fast food restaurants now that have plant-based, you know, burgers and stuff that are way better for you, right? All right. That was a little bit of a detour. So what we're doing here is we're going to try to figure out all the different forces that act on beam A, B, C, D, E, G, right? So that we can then figure out the with these functions for shearing force and bending moment as functions of where we are located along the x direction. Does that sound good? What's our first step, you think? There's a free body diagram. You guys are getting good at this, right? You know how to answer. So let me do a free body diagram of this thing. Let's see. Nice, clean free body diagram. All right. Now, let me actually start, before I draw this free body diagram of this piece. Let me just convert this thing into a free body diagram. I can do that by just erasing those supports, replacing the roller with one force that would be perpendicular to where it was acting. I'm going to call that RGY. What should I do at A? Okay, RAY. And I could show an X direction reaction as well. Do I need it? Okay. It can be there if it needs to be, but I have no forces externally acting on this body that would try to drive it left or right. I'm just going to leave it off for simplicity. Okay? So if that's what I've got for that free body diagram, let's use that to figure out my, my reactions at my supports first. Okay? My question for you is this. Do you even need to write equations at this point? Okay? I hear one vote for yes. Since there's a vote for yes, let's do it. We'll do it quickly. All right? So let's sum moments around A. Okay? If we're summing moments around A, we'll have a negative 50 pounds. How far is the line of action of my 50 pounds away from point A? And this is a little tricky. Okay. Okay, he's saying, could it be the distance from E to A? Keep in mind, what we're doing at this stage is we're leaving that entire body together as if it's a rigid thing, which means I need to just look at external forces to that body, not internal ones. The force that acts at E is internal at this point. Okay? So I need to look at just external forces. So I need to look at just the 50 pounds that pulls on the rope. Okay? And if you look, there's a elusive little piece of information. It tells you what the radius is of that pulley, which tells you if the radius is 1 inch, it shifts the line of action of the 50 pounds 2 inches away from E, right? So if I add these up, I've got 8, right, plus 6 would be 14, plus 6 would be 20, right? Plus 4 would be 24, plus 2 would be 26. Okay? Then what? Okay, I would say it looks like we were at 24 right here, plus 9 would be what? 33 inches? Okay, got to be careful there, right? All I need here is the distance from G to A. Remember, 26 was this distance. Exactly, yeah. So I'm going to take 24 inches plus 9 gives me 33 inches. All right. This is equal to 0, and I can solve for this to find RGY. RGY just ends up being 50 times 26 divided by 33. 39.4, we'll say. Okay, units, pounds. So let me put that right here. 39.4 pounds. What's RAY? Okay. All I have to do for RAY, some forces in the y direction, and I'll have RAY, okay, minus 50 pounds plus 39.4 pounds is equal to 0. And out of this, I can get RAY is going to be equal to 50 minus 39.4, which gives me 10.6 pounds. Okay, so let me put that in over here. Excellent. Yeah.
Why do we use 50 pounds being 2 inches past the E? I thought we were able to reduce the force to the pin at the pulley.
Okay, his question is, why did we put the force along the line of the rope where the force is being applied? He said, I thought we could replace that with forces acting at the pin of the pulley. The answer is yes, you can, but you got to replace the whole rope. Like if you decide to take the rope off of there and replace it with something else, it means you've got to take the rope off. You've got to put 2 forces of 50 pounds downward at I, and you got to put 1 force of 50 pounds upward at E. Because if you decide to remove the rope, you got to actually remove the rope and replace all the effects of the rope with what those effects would be. The other option you can do is you can leave the rope on. And as long as you know the line of action of where the force is being applied to the rope, then everything else becomes an internal force to the diagram, and you can just let it be. Does that make sense? Okay.
It's 100 pounds at point I because the rope pulls on.
Yeah, there's 2 locations where rope comes down off of the pulley at I. So I'd have to put both of those 2 50-pound forces at the pin at I, and I'd have to put 1 50-pound force at the pin at E. If you were to do that and then do the same thing that I just did, it would end up with more terms in it, significantly, but you'd come up with the same external reaction values. All right, so there are my external reaction values, and since this is, becoming second nature, hopefully, to you by now, let me get rid of those and just remember that those are my external reactions that I have at A and at G. So now what? Okay, I started drawing one of my free body diagrams down here, which evidently my computer does not like to let me move it easily, but there it is. All right, what are my other diagrams that I might need? Okay, I could think about the location of the pulley, or I could just remove the pulley and think about the member that the pulley is connected to. So let me actually do that with this member. What member you think I'm drawing here? Okay. And I've got at B a pin, right? And let me show a force coming down at this location. I'll call it BY, right? And if you want, I can show one that goes in the X direction as well. All right, let me also add something here that says this compliant material. Actually, let me say what a compliant material is, right, real quick. I gave you the example of like hamburger meat, right? How does hamburger meat strike you? Squishy, someone says, right? Easy to deform, right? That is, if you want a technical term for something that's easy to deform, you can use the word compliant, right? Compliant is the opposite of stiff, all right? So that's a compliant material, something like hamburger patty. Let me give you another piece of assumption that maybe you wouldn't think of. Let's assume that that hamburger patty is not applying any kind of a horizontal reaction, all right? And I'll give you the idea here that there's not much that would ask it to apply a horizontal reaction, so let's just assume it has zero horizontal reaction, okay? What direction do you think the force would act at pin H on body BHI? All right. I would say it looks like a force would act upward like this. The reason I know that is I can do another maybe simplified version of the little shoe thing that's pressing on the meat. And I would say the way I would model that is with a distributed load along the bottom side of the shoe. Okay. With a force acting downward like this. Okay, let me call this maybe just RH. Okay, and what other forces should I apply to this little lever? Okay. At the pulley, we mentioned this a second ago, I can show it as two different arrows, or I can just show one arrow down that has a force of 2 times 50 pounds. Pulling downward out there on the end of that lever. Okay? Now, the dimensions that might matter to me are these, right? The horizontal direction is really the main thing that I'm concerned about with this problem. So how far is it from B to H? Looks like it'll be 11 inches, right? How far is it from H to I? Be careful, right? It looks like it might be 10, but you got to remember the radius of the pulley, right? This is not a small pulley. This is a pulley where you're given the size of it, so you probably should consider the size of it. Okay? So it's another 11 inches here. Okay? Now what can I do with this diagram? What if I sum moments around B? Okay? What I will have there is negative 2 times 50 pounds times what? 22 inches, right? What else would I have that would create a moment around B? RH. Okay? So RH, positive, right? Positive RH times 11 inches. So RH would be what? Okay? Pretty easy, right? But I'll go ahead and do it out here. 2 times 50 times 22 divided by 11. Right? 200 pounds. Okay? Let me also do a sum, while I'm on this diagram, a sum of forces in the y direction. And there I will have minus by plus this 200 pounds that I just found for RH pushing upward, right? Then I have minus 100, or 2 times 50 pounds. And all this is going to be equal to 0. So what's by? Okay? Now what about bx? Okay? As long as I'm assuming that that compliant material isn't reacting anything in the horizontal direction, then we can easily just say, let's say bx is also 0.
If we found out that like our compliant material did have an X component, would we just do a moment about B?
Okay? Her question is, what if we figured out that that assumption was bad? Like you had that compliant material in there and it actually was pushing left or right. I would say we would actually need another piece of information before we would really know what to do. Because we would have to know exactly what that reaction was doing. And right now I don't think we have enough information to be able to assume anything about that. That's another good reason to make the assumption that there's not any at this point. You know, maybe that's actually not a good reason to make that assumption, but it helps us out to make that assumption. There is a good reason to use it, and it's that based on our understanding of how like hamburger meat would happen underneath this press, there probably wouldn't be a significant amount of horizontal reaction that would be happening in that material. Okay, so now we have an RH that's 200 pounds. What do you think this distributed load is going to be on the underside of this shoe? All right. I made the numbers pretty nice for you, right? How long is the shoe? 12 inches long. It's 1 foot long, right? So you could say it's 200 pounds per foot if you wanted. Or, since actually we've got everything else in inches, it might be a good idea to leave it in pounds per inch. What would it be in pounds per inch? Okay, 200 divided by 12. Okay, which would just be 16.667 pounds per inch. Okay. We did the machines part of this problem just now. What do you think I'm going to do with all that information? Okay. Let me redraw. I don't know what it is about moving this little piece right here, but it doesn't like me to select it. Okay, let me draw an updated diagram of beam AB, CD, EG with just the forces that act on that body. Okay? So, at A, I have an upward force of 10.6 pounds. At B, what do I have? Keep in mind, BY right here was what? 100 pounds? So what should happen at B for the other part? Equal magnitude, opposite direction, right? So I would have an upward force here of 100 pounds. Then what? Yeah. Okay, just like every other time, if you assumed this force had gone the other direction, okay, let's say you had assumed it went this direction instead, you would have done your math over here, solved and gotten a negative answer, and you would have said, my force doesn't really go that direction, it goes the other direction. And you'd end up with the same conclusion about the force that the direction goes on part A, B, C, D, E, G. Okay, so here's where it might get a little bit more tricky. Not really, a little bit. Between C and D, we just assume that that same distributed load happens across there. Okay, so that's 16.667 pounds per inch. What do I do next? Do I need to do anything where the rope connects at E? £50 up right there. Then what? Okay. A reaction force upward here of 39.4 pounds. And all that stuff that we just did, that is stuff you should expect that, you know, in a real world kind of scenario, you might have to do all of that just to set up this beam problem, right? In a lot of your textbooks, your beam problems are going to start with a picture like that I just drew, right? But sometimes it takes some thinking just to get the problem boiled down into something like this, where you have concentrated and distributed loads defined on a beam. Okay? Furthermore, let me go ahead and copy my lengths over here because they're going to be important, right? 3 feet. This was 5 feet, or it's not feet, inches, right? 3 inches, 5 inches. Okay, this is going to be 12 inches. This is going to be 4 inches. And this is 9 inches. Everyone good so far? Because we're about to go into our next phase. All right, what we're trying to figure out here, keep in mind, we're supposed to find functions for V as a function of X, shearing force as a function of X, and bending moment as a function of X. What is X? X is defined as basically our location along the length of this beam, where 0 is considered to be this left, coincident where that left support is. So this is our X direction. And so we're going to try to find these functions as functions of the location along the X. Okay? Now where shall we start? Okay? Here's what we got to do. We got to make cuts in any segment where we think, we don't have a lot of changes happening. We got to make a cut between two places where we're saying, hey, there's not really any changes happening in this segment, right? So the first place I would identify that would be like that would be to make a cut in that leftmost segment somewhere. And when I make that cut, I'm going to draw a free body diagram of one side of the beam or the other. Which do you think would be easier for that cut? Okay, the left side might be easiest, I think. So let's make a little three-body diagram of just that left side. All right, and when we do this, what we're going to do is put all of our externally applied loads, right, on here. One of them is going to be this 10.6 pounds. How far is it from where that 10.6 pounds is applied to where the cut happens? Okay, X, right? So we'll say X is the distance from here to here. Wonderful. Now, here's where you need to be careful with your sign convention. What I recommend that you do is always draw your V and M reactions at the cut according to positive sign convention. Assume they are positive. What happens by doing it that way?
It's negative, and no, it's negative.
Right? Yeah, well, once I solve for it, then whatever I get as my function, I can just put in as my value for that function for this domain, which, by the way, I meant to put that up here. What I'm doing here is only valid for x between 0 and what? 3 inches. Okay, so I'll say what I'm doing right here is for that little range. Okay? So to put positive sign convention for my reactions at the cut, what direction should I draw my, my reactions there? What for shear? Okay? Go back up, and this is ways up here, right? But we said that on the left piece, if you have a down arrow, that is considered to be positive shear by our convention. So I'm going to assume a down arrow and call that V. Okay? And what should I do for my bending moment? Counterclockwise. Okay? So there's my, my little free body diagram. What is M going to be? M is going to be equal to 10.6 pounds times what? Okay? And because I did this in terms of x instead of a specific length value, I'm going to say that's M of x. What about V?
It's always
10.6 pounds. And even though it is constant at 10.6 pounds, it is true for any x in that range. So it would be valid for me to say this is V of x, even though there is no x in the function, right? Okay. And I kind of went out of, I'm going to do most of these where I do the V first instead of the M.
Should the Vx be negative?
Should what be negative?
Vx.
Okay. Question is, should Vx be negative?
Or is it you guys were doing estimating positive convention? Right.
Okay. Question is, we assumed positive convention, right? So the question is, should V of x be negative here?
We're assuming positive shear, so the force is negative.
Okay.
Positive shear, is that right?
Yeah, if I was to sum forces in the vertical direction, I would have 10.6 minus V equals 0. So V would be positive 10.6,
Okay.
right? And, you know, so then it turns out to be this positive number. We assumed it was positive. So we can actually conclude here, yeah, there's going to be a positive shearing force in this segment of the beam. Easy, right? You think it might get harder? Yeah, a little bit. Not too bad, though. All right. So for the next one, what do you think our next little segment is going to be? Somewhere in here, right? We're going to pick some location between the 100-pound force that I put right there and the distributed load that I start at the left end there. So what would that free body diagram look like? Okay, now, while you're thinking about that, I'll say for what? X greater than 3 inches. and less than 8 inches. Okay? Here's what the free body diagram would look like. We would have 10.6 pounds here. We would have 100 pounds here. There would be 3 inches between those, right? There would be X to where the cut was made. We're going to assume our positive sign convention, right? V and M. Okay? And I'll go ahead and do these out. What if I sum forces in the y direction? 10.6 pounds plus 100 pounds minus V equals 0. Tells me what? V, which again would be V of X, right, is going to be equal to, okay, 110.6 pounds. Now what if I sum moments here about the cut? Right? I would have minus 10.6 pounds times what? Times X minus 100 pounds times what? Okay, X minus 3 inches. Then what? Plus M equals 0. And this tells me what? M of X is going to be equal to, okay, 10.6 pounds times X plus 100 pounds times X minus 3 inches. I think that's it, right? So those would be my shear and bending moment functions in the range of the beam from 3 inches to 8 inches. Easy stuff, right? Where's our next segment? Okay, we got to pick somewhere now in the middle of this distributed load. Right? And we're going to say that our little domain we're working in is going to be between 8 inches and what? 20 inches? Okay. Here's what the free body diagram would look like. We're going to have 10.6 pounds. We're going to have 100 pounds here. And we're going to have a little portion of the distributed load happening over here. Okay, which is going to be at 16.667 pounds per inch. We're going to assume our positive sign convention again, where I've got a downward V and a counterclockwise M. Okay. What about my lengths? Okay. I have a distance of X from the 10.6 pounds to where I'm doing the cut. Right? I have 3 inches to the 100-pound force. I've got 5 inches to the beginning of the concentrated load. Okay. So what's the length of the concentrated load section, or the distributed load section? This will be x minus 8 inches, right? That's how far it is over that range. So how much load do I have there? Okay, and I'll mark that on here like I do a lot of times. Okay, something like this. What is my lumped load for that little segment of distributed load? Okay, 16.667 pounds per inch times x minus 8 inches. And how far is the line of action of that lumped load away from the cut? X minus 8 inches over 2. Okay, and all that was kind of important for me to work through because it's going to make drawing or writing my equations easier. So let's write these equations. Okay, summing forces in the y direction. I have 10.6 pounds plus 100 pounds, right? Minus what? 16.667 pounds per inch times x minus 8 inches. Tell you what, I'll put this on another line right here. Then what? Minus v equals 0, which tells me that v is what? V of x will be, okay, I'll use the same value here, right? 110.6 pounds minus 16.667 pounds per inch times x minus 8 inches. Say what? Do we need to distribute the 16.667 across the x minus 8 inches? We don't need to. I mean, you can, but you don't need to. All right? But you're probably noticing here that this is our first instance where our v of x function has actually been a function of x, right? Where x actually is a variable included in it. That's kind of interesting. Now, for our big one, right? The moment equation. I'm going to give myself some room down here. What if I sum moments around the cut? What will I see here? Okay. Minus 10.6 pounds times what? X. Okay. Minus 100 pounds times x minus 3 inches. Okay. Plus, okay, this one's kind of the trickiest one, right? 16.667 pounds per inch times x minus 8 inches times x minus 8 inches over 2. Okay. And this gets a little bit confusing because what we did here is that basically this much came from the concentration of the load, the lumping of the load, right? Whereas the other part, this part right here, came from the distance. But you'll see there they both contain an x minus 8 inch, so a lot of times people will put that together and let it be a squared term, right? But I'm going to leave it like this so that you see where it came from. What else do I need in my sum? Plus m is equal to 0, and what that tells me here is that m of x just ends up being 10.6 pounds times x plus 100 pounds times x minus 3 inches. So then what we'll do is we will add, or subtract, excuse me, 16.667 pounds per inch times x minus 8 inches squared over 2. All right. We've got a couple of more little segments to do. You got it in you? Okay, you guys are tough. What's our next little segment you want to do? Okay, after the distributed load, we're going to make our cut now here. So this will be for x between 20 inches and 24 inches. Yes, sir. His question is, do we need to keep doing our free body diagram relative to the left? I will say the answer is no. You don't always have to do it relative to the left. There is a nice advantage of doing it relative to the left, and it is that one of your dimensions will always just be x if you always do it relative to the left, and you've defined your x that way, right? Which we have. We've defined our x relative to the left end, and so there is something nice about doing it relative to the left. I'll tell you what. I'll do this one as my last one relative to the left, and I'll show you the last one relative to the right. Okay? All right. We got to be quick here. So we got 10.6 pounds, 100 pounds. We've got our whole length of our distributed load, 16.667 pounds per inch. We've got our positively oriented reactions. We've got our length of x. We've got a length of 3 inches here. We've got 5 inches here. We've got 12 inches here. Okay. We can lump all of that distributed load right at the middle of that little piece. And that, what is that going to be? We could calculate it again if we wanted to, but you might remember a calculation we did that was similar. 200 pounds, right? That is the total amount of force being applied over the entire hamburger patty, right? 200 pounds being applied right there. And how far is that away from the cut? Okay. What it's going to be is, okay, x minus 3 plus 5 plus 6, right? Which would be what? 3 plus 5 would be 8, plus 6 would be 14, right? All right. So let's quickly do these. What is my v function? I would sum forces in the y. Okay. So I would have 10.6 pounds plus 100 pounds minus 200 pounds minus v equals 0. So what is v going to be? Okay. I mean, v of x, I'll tell you what, you don't even have to simplify these out if you don't want to. You can just kind of leave them alone. So what that would be is just 110.6 pounds like we had before minus 200 pounds. Okay, what about m? Again, we're going to sum moments around the cut. Okay, and when I do that, I will have 10.6 pounds times x plus 100 pounds times x minus 3 inches minus 200 pounds times what? X minus 14 inches we figured out a second ago. Okay, plus m equals 0.
You jumped straight into writing your m of x, didn't you? Because those moments should be negative, the first two.
I may have. Hang on. You're right. Minus, minus, plus, plus m. Thank you. Yeah, I immediately started thinking of clockwise as positive, even though I said I was going to do counterclockwise as positive. I'm sorry. All right. So then that means m of x is going to be equal to 10.6 pounds times x plus 100 pounds times x minus 3 inches minus 200 pounds times x minus 14 inches. Okay? So probably nothing surprising there. Now, I told you the last one I was going to do to where I drew a free body diagram of the right piece. Okay? Like the rightwardmost piece. So let me draw this arrow over to some cut that we make in that last segment. But this time, I'm going to take the segment of the beam to the right of that. Okay? Now here's what's tricky. My x value is still measured relative to something over here on the left. All right? And how far is it from that same line to my 39.4 pounds that I have on the right side? Okay, I don't necessarily expect you to remember it, but it was 33 inches to that location. So what's this little length right here?
33 minus x.
All right, so that's one thing that's tricky. What's the other thing that might be tricky? Okay. I have to use positive sign convention whether I'm doing the left side or the right side. If I'm doing the right side, what does positive sign convention look like? Opposite of what I was doing on the left side, right? So where I used a downward V, up here I need to use an upward V to assume positive sign convention. And what do I need to do for my moment to assume positive sign convention? A clockwise M. Okay? So what is my v of x function going to be? negative 39.4 pounds. How did I see that so easily? Okay. Both of those arrows go the same direction, which means V must actually go the opposite of that direction that I assumed was positive, right? What about M of X? Okay, M is going the correct direction, and so we'll have 39.4 pounds times 33 inches minus X. And I know everyone is itching to get out of here, but I want to show you one last thing that you're going to like, okay? Because we just came up with our last function, our last set of functions for shearing force and bending moments in beams, okay? Here's what I want to show you. Got this thing over here. I can plot these suckers. And I want to show you what they look like underneath this beam. Okay, I'm going to line it up somewhat right. These are the functions that we just found. Do they look like they are related at all? Okay, get your calculus hat on. Do those two curves look related? The upper curve looks like the derivative of the lower curve, right? Crazy, right? If you're curious where I got this from, I loaded all these into a MathCAD sheet, real MathCAD, not fake MathCAD. Okay. I loaded these piecewise functions into this MathCAD sheet so that it would show what these functions look like, right? And that's what they look like. Okay. So I'm going to get your appetite a little bit stirred up for our next meeting, because our next meeting, does this feel like this was pretty tedious? Our next meeting, I'm going to show you how you can draw these curves based on just a few principles without having to do very much math at all. You'll have to do some, but it's a lot less math than what we just did. I'll see you guys when we meet again.